Good evening, everyone present. Today we shall carry forward our discussion on the various types of special concrete, and we shall enter now the fifth week lectures. Okay, so today we shall be basically focusing on self compacting concrete (SCC). Okay, so it is a special type of concrete. Okay, so we shall study what are its characteristics, what are its conditions, parameters, applicability, usefulness, and various other stuff, and also the tests, okay, associated with its quality control. So if we can see here, okay, two structures are shown, okay, which are having honeycombing, okay, during its construction. So as we all know, honeycombing it is results mainly due to the improper compaction of concrete, and also if you see here, there will be a higher density of reinforcement, okay, which is also adding to inefficient compaction, okay, resulting in honeycombing. So as I told you, so here the density as you can see in this pic, the density is quite high of the reinforcements. So because of this reason, the placing of concrete is not that easy, okay, which will not allow proper compaction, and therefore the the quality will deteriorate, okay. So premature deterioration observed in several reinforced concrete structures, okay, so that is mainly due to workmanship, okay, one of the reasons, which is identified as principal weakness leading to poorer quality of concrete construction than anticipated or designed for, okay. Secondly is the lack of vibration or over vibration identified as a major source of weakness in concrete construction. Thirdly, the dense reinforcement, which makes it difficult to place and compact concrete in several reinforced concrete structures. So these are some of the reasons for the premature deterioration. So other than strength, placeability, constructability, and compatibility are identified as independent parameters for performance of concrete. Research in high performance concrete focused on basically two dimensions. Okay, so one is self consolidating concrete, okay, which is also known as self compacting concrete, and second is high strength concrete. Okay, the two dimensions are basically independent to each other. So fluidized concrete with no segregation that self compacts under its own weight, okay, without the need of any external work such as a vibrator machine, okay. So that is an example of self compacting concrete, okay. So it eases placement and ensures consistency in quality independent of worker skill, saving time and manpower, okay. Casting in complex forms, okay, gives it enables the casting of complex forms, okay, thereby giving the freedom in the structure design, okay. Enables construction under hazardous environment, okay. So these are some of the utilities, okay. These are some of the basically the utilities of this one, the self compacting concrete, okay. This, okay, we also need to study, basically view the proportioning of the appropriate mix, the long term mechanical properties, the early age strength, toughness, volume stability, and service life in the severe environment, okay. So basically the characteristics of self compacting concrete, okay. So in the fresh state, these four are basically the main parameters, okay. The filling ability, passing ability, segregation resistance, and viscosity, okay. So these four parameters, okay, they are basically related to the workability, that's why it's called fresh. So these are the important characteristics of fresh SCC, self compacting concrete, okay. So the concrete mix can be classified as self compacting concrete if it possesses the adequate properties related to filling ability, passing ability, segregation resistance, and viscosity, okay. And to check all these parameters, there are various tests which have been defined, okay, according to the suitability, and we will go through all of them in a short time, okay. So if we go through our previous discussions, okay, uh, these are the main mantra, okay, of concrete. So basically paste is nothing but water plus cement, okay. mortar is the addition of fine aggregate to the paste, and concrete is the addition of coarse aggregate to the mortar. Okay, and if we define it in a standard way, we can say that concrete is a suspension of coarse aggregate in mortar, mortar is a suspension of fine aggregate in paste, and paste is a suspension of cement in water. So all these definitions and concepts we have gone through in the previous classes. Okay, so all the three can be modeled as a combination of a fluid and particulate phases. Okay, so we have even gone through the schematic diagrams, okay, and their representations, how that can be achieved. So as you see, this material which is paste, okay, so it has the combination of cement particle, okay, which is mixed in the water, that is the paste. Okay, similarly mortar is the mixing of the sand particle, okay, in the paste. Okay, and concrete is again the suspension or mixing of coarse aggregate in the mortar. Okay, so here the star mark indicates that this cement is basically it refers to the cementitious material. Okay, so that means it can be cement, it can be any pozzolanic substance. Okay, so like cement, it basically refers to the powder content. Okay, the cementitious material content in case of SCC basically. So the presence of cement particles in water changes the characteristics of the latter. Okay, so this depends on the amount of powder and its properties. Okay, so basically the letter is basically signifying the mixture of this one, the paste basically. Okay, so different quantities, as we all know. So this presence of cement and water in various proportions will lead to various water cement ratios, which will indirectly mainly affect the strength, as we all know. Okay, so that's why the amount of powder and the various other properties play a significant role. So this leads to the idea that for a paste we can talk of a water powder ratio from the point of view of concentration of cement particles in water as modifying the properties of water, okay, and not strength development. So in case of self-compacting concrete, basically the main issue, okay, so main issue is related to the workability. Okay, so because it is self-compacting in nature, the workability has to be very fine. Okay, so because of that we mainly, okay, mainly we are concerned about the concentration of cement particles in water. Okay, so how to make it efficient and more ensure that it is adequate for our use. Okay, so extending the argument, we can consider mortar as a fluid, okay, whose properties are modified by the presence of sand, and the extent of modification depends on the properties and the volume of sand used. Okay, so basically these are very basic definitions. We will now see how the effect is going to be. So mortar is, as we know, composed of sand. So to make it a fluid and various other to go through the various other parameters, we have to modify the mortar and see how the properties get affected by changing the parameters. So we will be going through all those in a short time. Okay, so the extent of modification depends on amount of sand being added to paste. Okay, in other words, the properties of the mortar are a function of the properties of the paste and the concentration of the sand. Okay, so that is very much trivial. Finally, we look at concrete. At that level, the properties of mortar are being modified by the presence of coarse aggregate. So definitely coarse aggregate is a suspension of mortar. Concrete is a suspension of coarse aggregate in mortar. So at the level of concrete, the properties of both mortar and coarse aggregate are important, and basically the coarse aggregate modifies the properties of mortar. Okay, so the properties of the concrete are related to the properties of mortar and concentration of coarse aggregate. So this concentration of coarse aggregate is the basic parameter which defines the self-compacting concrete. Okay, why, we will see now. Okay, so what is SCC? So it is a flowing concrete which which does not require any additional external work for consolidation. So there is no requirement of any external mechanism or machine for compaction or consolidation, such as vibrator. Okay, so it consolidates under its own weight. Okay, that is the basic property. Fluidized concrete with no segregation and does not require any external work or vibrator, eases placement and ensures consistency in quality independent of worker skills, saving time and manpower. Okay, so These are a few of the very important advantages of using SCC. Basically, in case of reinforcement, okay, which is having a higher density, like very close spacings and everything. So very, which is having very less center to center spacing. So there the placement is a very big condition, as we saw in the initial picture of honeycombing. So that's why there the use of SCC is, is a very good alternative, a good solution. So casting in complex forms giving, it helps, like it allows the casting in complex forms giving freedom in design of structures, okay, as we also already discussed. And it enables construction under hazardous environments, okay. So various environments will like have will pose various challenges, okay. So there also this SCC can be of very good use. So advantages of working with SCC. So basically, what are the advantages? Let us see. Its highly fluid nature makes it eminently suitable for placing in difficult conditions, sections with congested reinforcement, hazardous environment, etc. So these are the advantages because of its high fluid nature. It can flow through tight sections comfortably as opposed to normal concrete, provided the mix is designed appropriately. So as we saw in the initial picture, as you can see here, so these are the issues. These are the cases where the concrete can properly flow. Okay, if it is normal concrete. Okay, so that is leading to the segregation and honeycombing. Okay, so these are its utilities. Then thirdly, it reduces the noise level at construction sites by eliminating the use of vibrators for compaction. So it is self-explanatory. If there is no external equipment used for compaction, it will definitely reduce the noise level at the construction sites. So it is its utility. Okay. And fourth is more rapid and consistent construction. Okay, because we don't need any external machines, equipments, or any external parameters are not involved, so it will result in much more rapid and much more consistent construction process. Okay, so let us see what is flowing or high workability concrete basically signifies. Okay, so it the flowing or high workability basically signifies normal unrestricted flow. Okay, so the flow should not stop after a certain point. Okay, it should go to a large, the flow should be to a very large extent, very large. Well, the slum value should be very much higher as compared to normal concrete. Okay, in like it should be almost around 10 times that of normal concrete. Okay, so that is one of the parameters. Second is the flow in closed spaces. Okay, as we saw just now, it is one of the requirements, such as in pipes during pumping, etc., or through reinforcement, as we saw in RC construction. So that is also one of the parameter for flowing or requirement for flowing or high workability. Okay, third is the segregation and aggregate interlock are of major concern. So where the segregation and interlocking, aggregates interlocking is one of major concern, there also it is very much useful. Okay, because of the compaction related issues. Okay, so to achieve all this, basically we go through these properties. Okay, so there were actually four properties if we have gone through. Yeah, so fourth was the viscosity, but basically they have shown these three properties as the important ones. Like one is the filling ability, one is passing ability, and third is the segregation resistance. Okay, so for flowing or highly workability nature concrete, so we have to go through all these parameters. So this should the concrete should satisfy these three basic parameters in addition to viscosity. Okay, so we will see how the test is done and how the quality control is achieved. Okay, so concrete flowing pipes. So basically in the case of pipes, okay, what is happening is there is friction in the surface, in the interface. Okay, as you can see here, because of some roughness or various other issues, so there is friction on the interface. So because of this, as we all know, velocity profile is related to the flow rate. So from fluid mechanics, so concepts of fluid mechanics, and this one dynamics. So we know that velocity profile is related to the flow rate. So the properties of the profile are related to deformability and other properties of fluid or liquid phases. So a lot of properties affect the profile, okay, profile of the velocity profile. So wow, friction in the interface or the viscosity, okay, and also because the concrete is a, although we assume it to be a homogeneous mixture, but it is basically a heterogeneous mixture. So because of that also various resistances are there, which results in velocity profile which is a little bit different, and also the issue of deformability and the workability arise. Okay, so we will go detail about that. So if we go into the case of friction, which is at the interface, so we will see that it results in deposition of some material, basically the mortar, okay, on the surface, as shown in the red color. Okay, so the deposit may also contaminate subsequent batches in RMC equipment. Okay, so it may result in blockage. Okay, blockage, and that may also add to the it may also increase the amount of segregation, okay, that is occurring. So this deposit must be cleaned at the end of the concreting operation. Okay, so after one use, effort has to be made that it is cleaned, okay, before and after use. Okay, the properties of first batch may be slightly different from those of subsequent batches. So the main issue is, like, because when the initial this one batch is flowing, so this deposition, okay, so this deposition will be there. After that, the after that deposition is saturated, okay, so no more additional layer is formed, then the concrete will be uniform. But at the first layer, okay, at the first flow, so because of the segregation, okay, that's why there are chances that the properties of the concrete flow are different. Okay, so that also that may also give a question, like, is it will there be any requirement for running a priming batch? Okay, like before before the actual concreting, is there any requirement for running a mock flow? Okay, so that this deposition, okay, this is taken care of, and basically it is coated. Okay, or is there need for any layering, okay, painting or something which reduces the this one, the friction. Okay, so all these are matter of concern, okay, and which is dependent on the site conditions. So segregation, what is like basically how it is affecting, let us see. So it depends upon the properties of the fluid medium. Okay, only a certain volume fraction of particular particulate material can be carried. Okay, so that is the one of the reason for segregation. So it is basically the settlement of heavier particles from the fluid phase. Okay, so if we remember that all constituents used in concrete, which is basically sand, cement, coarse aggregate, and water. So sand, cement, and coarse aggregate all are having some the all are heavier. Okay, as can be found from the this one, the specific gravity values. So all are having value greater than 2. Okay, so sand and coarse aggregate is having around 2.65 to 2.75, and cement is around 3.15. Okay, so those are standard values, but all are greater than water, which is 1. So we all know, so they are heavier. Okay, and water is the only liquid used in the system, so therefore there is a tendency of heavier particles from the fluid phase to settle down. So this volume fraction is also related to the properties such as density, shape, size, etc. of the particular particulate matter. Okay, so because of the heavier particles, okay, and the settlement, okay, so only a certain volume fraction can be carried. Okay, and that is also dependent on the density, shape, size, and various other criteria. Okay, so again, if we go into the case of aggregate interlocking, so we will find that the susceptibility for interlock, okay, so that depends on the ratio of the size of the opening through which the concrete flows. Okay, so it is also related to maximum size, shape, and the volume fraction of the aggregates. So the this one, the opening size and various other parameters. Okay, so that will also depend on that will also play a major part for the interlocking this one, susceptibility. Okay, so all these criteria have to be kept in mind. So now, if we look at the properties of concrete in that perspective, it can be said that in order to get a certain property in the concrete, we need to ensure a certain property in the mortar, certain property in the aggregate phase, and that the concentration of the coarse aggregate should not exceed a certain level. In other words, for a given nature of aggregates, we can have a critical maximum volume beyond which a normal motor is not suitable. Okay, this maximum level is a carrying capacity of the fluid phase. So as you saw in the last diagram, okay, so here as has been discussed, okay, so the opening size matters a lot. Okay, so if the size is very less, okay, and you are having lot of if the size is less, then definitely the amount of aggregate will be high. Okay, and if there is more aggregate, so there will be definitely lesser interlocking because of lesser presence of binder. Okay, but if you see here, if the as compared to this, if the either the size of pore is large, or in this case the aggregate content is less, so there is mortar everywhere. Okay, so that results in a good binding and aggregate interlock. Okay, so that those criteria are of prime significance. That's why this one, the properties of concrete, okay, so they matter a lot. Basically the property of mortar, property of aggregate phase, and the concentration of coarse aggregate. Okay, so it should not exceed a certain level when flowing through a pipe. Okay, so that value, okay, so that value of maximum level of coarse aggregate is basically called the carrying capacity, okay, of the fluid phase. Okay, so that is the critical maximum volume, okay, beyond which a normal motor is not sustainable. So we have to take into account all these factors. So now let us go through the consequence of paste. Okay, cement is of course the fundamental ingredient for cement paste in the context of concrete engineering. Indeed, other materials can also add to the powder volume and concentration of these materials, such as fly ash, blast furnace slag, also contribute to strength development, but those as stone dust contribute only to the powder volume, because the main factor is the is that the this one, the strength is mainly given, as we you might know, the strength is mainly given by the calcium. Okay, the calcium composition. So this if we go to the standard cement OPC, so that basically contains around 60% of this one, 60 to 65% of calcium. Okay, calcium oxides, and then around 18 to 20% of silica. Okay, so this the strength of the binder is mainly given by the calcium. Okay, if we go in the case of fly ash and blast furnace also, the calcium is lower than OPC, but still it is having a substantial amount to provide the strength. Okay, but in the case of stone dust, okay, because there is no calcium component, so that will only contribute to the powder volume, it will not contribute to any strength. Okay, so simply increasing cement content to increase the powder volume has obvious undesirable effects. The main undesirable effect is that there will be no strength development. Okay, it will just act as a filler. Okay, so filler is already acted the act of filling is already done by the sand. Okay, so that's why we have to take into account that parameter also. Okay, increasing the powder content in paste increases its carrying or holding capacity, and also has the effect of increasing the mortar content in the concrete mix. So if the criteria of this cement is satisfied, then the powder content increase, okay, in the paste will definitely increase the carrying or holding capacity, and it also has the effect of increasing the mortar content. Definitely, if this is increased, the mortar content will also increase, which will result in the increase in carrying or holding capacity. Okay, so another route available for modification of paste properties is the use of chemical admixtures such as superplasticizers or viscosity modifying agents. So these two type of chemical admixtures, so basically superplasticizer and plasticizer, we all know, so that basically results in more workability at a reduced water content. Okay, so if we want to keep reduce the water content and cement ratio and keep the slump value same, then we can use superplasticizer. Okay? And viscosity modifying agent is basically quite the opposite. Okay, so this is mainly used for increasing the viscosity, okay, the friction between the proper materials. Okay, so like it will not allow easy flow. Okay, so superplasticizers help us in increasing the cement and or powder content at a given water content without compromising the workability of the mix, as just I discussed. So it is basically used for reducing the cement and powder and water content without reducing the workability, maintaining the same workability. And viscosity modifiers can be used to engineer the viscosity of the paste, that is, through their use, the water content in a mix can be increased without increasing its susceptibility to segregate by increasing the viscosity. So if we use viscosity modifiers, VMA, so what will happen is that we can use the water content, but we don't have to fear about the segregation part, okay, because of the increase in friction, okay, in fluid friction, which is definitely viscosity. So because of that, even at higher, if we even increase the water flow, the water content, then also there is, we don't have to get afraid of the segregation part because of the viscosity agent, okay. So how they are useful, okay, we will go through in the case of self compacting concrete. So self compacting compaction in a concrete mix is a balance between the fluidity and the resistance to segregation, okay. So these two parameters are the main parameters, okay, which can be tested by all the four parameters which we discussed, like the flowing ability, okay, passing ability, viscosity, and one more was there. So those parameters are, those tests are used for checking the fluidity and resistance to segregation, okay. So are they in at a optimized level or adequate level? So the fluidity is definitely, as we just studied, it can be achieved by using the superplasticizer, and the resistance to segregation can be achieved by using the VMA, viscosity modifying agent, okay. So we will see how. These are two essential and conflicting properties, okay, because they are quite opposite to each other, and a stable equilibrium between them has to be established. So as both, both contradict each other basically, so therefore there is a trade-off, okay. So we need to find out a balance, okay, so that it gives the best this one SCC. So mixture proportions for SCC differ from those of ordinary concrete. The former has more powder content and less coarse aggregate. So that is basically the ingredient, okay, the proportion of SCC. So it will have more powder content and lesser amount of coarse aggregate. So let us now see what are the ingredients involved in its manufacturing. So the self-compacting concrete, okay. So it basically involves what? Basically the four basically the four materials. One is cement, okay, that is at the heart. Second is the cementitious material, okay, so which is the fly ash, GGBFS, microsilica, etc. So they basically together can be called as the powder content, okay. Then we have aggregates, okay, and lastly admixtures, which are, as we discussed, superplasticizers and viscosity modifying agents, okay. So the cement, okay, let us go through cement. So cement, here we can it has been found that basically all types of cement can be used, okay, and it should have a content between 350 to 450 kg per centimeter cube, okay. So per centimeter cube of concrete, it should have weight of three, like amount of 350 to 450 kg should be used. Higher cement content can cause higher amount of shrinkage, okay. So that has to be kept in mind basically, because shrinkage, plastic shrinkage and every other parameters can come into play, okay, because of the voids, okay, the voids due to evaporation of the pore water, the capillary pore water, okay. So lesser cement possible with use of supplementary cementitious materials as seen. And also the cement content will, as we just as we studied last class, it may also increase the this one thermal cracks, okay. So higher, if we more, because it is an exothermic reaction, more cracks will develop. So all those are the issues, okay. Lesser cement possible with use of supplementary cementitious materials, SCM. So to counter that, we can take the help of SCM, okay. So, and also it has been found that it is quite advantageous. So cement content can be kept between 350 to 450, and other than that, the more amount required can be adjusted by using the SCM, okay. So if we see here, what are various types of supplementary cementitious materials? So they are basically fly ash, GGBFS, microsilica, etc. And it has been found that fly ash can be used preferably, okay. So it is because there are a lot of this one here, there are a lot of thermal power plants, so we can easily avail those, okay. So it improves the workability and cohesiveness, and reduces bleeding and segregation, okay. So these are some of, also some of the parameters of this, some of the characteristics of this SCM. It improves workability, cohesiveness, and reduces the bleeding, okay, the release of water to the top, and also the segregation, okay. So it improves durability and overall performance of concrete, we can say that. So that is all about cement. Now let us go to the aggregate portion. So all sound aggregates meeting the standards requirements are suitable in the case of for the case of SCC. They may be natural or crushed aggregates of any mineral composition. Okay, it can be limestone, dolomite, quartz, basalt, etc. So the maximum size of the aggregate is normally limited to 20 millimeters, and aggregate shape should be round or cubical. Okay, so these factors need to be kept in mind for for its use in SCC. Okay, so elongated aggregates do not produce satisfactory mix due to increase in internal friction. Okay, so this is one of the aggregates which which needs to be avoided. The elongated ones, we can go for round or cubical one. Okay, so elongated aggregates will not produce satisfactory mix because there is increase in the internal friction, which will maybe result in segregation, okay, or not proper flow. So that is basically about aggregates. Now let us go to superplasticizers. Okay, so superplasticizers are an essential component of self-compacting concrete. Okay, so basically some of the very common and famous superplasticizers are sulfonated melamine formaldehyde, naphthalene formaldehyde condensate, and polycarboxylic ether base. Okay, so these are some of the used superplasticizers by the industry. Okay, construction industry. So the water reduction should be more than 25%, allowing for a total water content of 160 to 180 liter per meter cube in the concrete mix. Okay, so the water reduction can be done. Okay, so it can be reduced to more than 25%, which will also help in reducing the cement content also. So that will allow for the total water content to be in between 160 to 180 liter per meter cube for the concrete mix. Okay, so this is some ideal this one value. And apart from that, let us go through the viscosity modifying admixture. So VMA, these admixtures are of various chemical nature and provide the correct rheological profile to the self-compacting concrete. Okay, so various chemical properties are involved in these admixtures. So they basically improve the segregation resistance of the mix without the loss of workability. Okay, so the segregation resistance, that is the main job of the VMA. Okay, and performance fluctuations due to variations in the material's quality and the moisture in the aggregates are attenuated by the VMA, making the quality control easy. Okay, so it also controls the performance fluctuation. Okay, due to the material quality variation and presence of moisture in the aggregates. Okay, so uh, here in the case of this one, uh, in the case of sand. Okay, so we use a term called fines. Okay, so how it is different from fine aggregate is that this fines is basically the material which is passing through 0.125 mm sieve. Okay, so fine aggregate, if we go through geotechnical classification, we will find that it is anything which is less than 4.75 millimeter, right? But here if we talk about SCC, here we denote fines as any material which is passing through 0.125 mm. Okay, the total amount of fines required in a self-compacting concrete depend on its fineness. Okay, so how fine the fines are, how much fine the fines are, that based on that the total amount of fines that is required for SCC is based. Okay, and basically it is around like as you will see in the coming example, it is around 8%. Okay, so 8% of fines are required. So it is inert as well as reactive aggregates can be used as fines. Okay, so both can be used. Pozzolanic materials will contribute to the strength development, and their effect should be considered in the mix design. So as pozzolanic materials contain calcium in small proportions, although like they have a sufficient good adequate calcium concentration, although it is less than OPC, so they will definitely contribute to strength development, and therefore their effect can be considered in the mix design. Okay, so the self compactability of concrete, as we discussed, okay, it is a trade-off between the two opposing properties. One is deformability and second is viscosity. Okay, so for increasing the deformability of the paste, we are using superplasticizer. and that will increase the water powder ratio basically. Okay, so that's why we reduce the water when we use super plasticizer. And secondly, if we are using adequate viscosity, okay, we're using VMA, so that will basically decrease the water powder ratio. Okay, so we need this one, we need the increase, we need increased deformability as well as increased viscosity, which are quite opposite to each other. So therefore we need to find out a optimum value, a balance value, which is as per our as per our requirements. Okay, so as you can see in this flow chart, so high deformability can be done by using superplasticizer, and high segregation resistance can be done by reduced water powder ratio, but both are opposite. Okay, so to achieve self compactability we need both. Okay, and apart from that, these two can be also achieved by using limited coarse aggregate volume. That's why the coarse aggregate concentration is quite low in SCC. So as you can see here, okay, so we can see the amount by percentage by weight, okay, of the individual constituents, and there's a comparison between the normal concrete and self compacting concrete. Okay, so if we see here, by percentage of weight, the water is almost similar, it is around 7%. Okay, but in the case of cement, okay, we will see that normal concrete, okay, it possesses a higher concentration, almost 14% by weight of cement, whereas in case of SCC it is around 7%. Okay, however it consists of blast furnace slag, okay, which is again almost 7%, and fly ash, which is around 9%. So 9 plus 7 plus 7, okay, it is around 23%, right? So this is total, it is coming to 23%, but in the case of normal concrete it is only 14%. So you can see a difference of 10%. Okay, almost 10%. So that's why the filling material is quite high, fine material is quite high. And again, if you come to the fly ash content, we will find fine aggregate content, sand content, we will find that in normal concrete it is around 28%. Okay, whereas in SCC it is around 33% also, that is almost 5% more. Okay, so here it is 9% more, the powder content total, and for fines it is 5%. So 9 plus 5, so almost 14% extra. Okay, so 14% of extra finer material as compared to normal concrete, and that's why the coarse aggregate value is also less by around 14%. Okay, so that is basically the, and this one the difference. Okay, so coarse aggregate is more around 51%, here it is 38%, so almost it is around 14% difference. So 14% more fine materials are present in self compacting concrete, and that is basically the difference. Okay, so here one thing we have to here, like the chemical admixtures are not shown. Okay, and that will also account into some more variations, and low coarse aggregate content is present, as you can see in SCC, which is around 14% less, and high fines and sand content is present in SCC. Okay, as you saw, around 10% more, 9 or 10% more. So that is basically in percentages of weight. Okay, if we see in percentages of volume, okay, there also we will find that water is almost same. Okay, 16%, but the cement, okay, cement, as we saw here, it was less by in terms of weight it was less by 5%. Here also it is more by 5%. Sorry, here also it is less by 5%. So the normal is around 10% volume, SC around 5%, and with the addition of 6 and 7% of slag and fly ash, it comes to around 18%. Okay, which is 1.8 times more than the powder content of this one, normal concrete. And if we take into sand, okay, sand is again 4% more. Okay, so 8 plus 4 is again 12, so 14% more, 12 and 14%. Okay, 14% by weight and 12% by volume. And here if we say the coarse aggregate, it is 11% less. Okay, so the total is 95 and 96%, and rest are probably the voids. Okay, so if you compare here the powder fine content, okay, one is having 10, okay, and one is 18, 5 plus 6 plus 7. So volume of water to volume of powder ratio, both are having 16% of water. Okay, by volume. So 16 by 10 is 1.6 and 16 by 10 is 0.89. So the water to powder ratio in self compacting concrete is lesser. Okay, then lesser than 1, and in case of normal concrete it is greater than 1. Okay, it is 1.6. so that is the like general this one general parameters, general values. Okay, so coarse aggregate is, again, as you saw, it is 11% less by volume in case of SCC compared to normal concrete. So these are the various parameters. So here basically they endorse the use of fly ash, pozzolanic materials and other thing along with the cement to increase the powder content and reduce the coarse aggregate. Okay, and also for sand they use fines. Okay, so all those we will see how they are implemented. So for making up a cubic meter 1000 liter of concrete, so this air, water, powder cement, sand and coarse aggregate. So this is conventional air entrained concrete. Okay, so this is typical self compacting high performance concrete. So here what we have to see is if like how the aggregate content changes with the type of concreting. Okay, so although it is low, like there are various many differences. Okay, there are again variations. Okay, so if the shape is very complicated and members are having narrow cross section, and the clearance between 30 clearance of reinforcement is between 35 and 60 mm, which is very less. Okay, so there again we have to further reduce the aggregate content to 0.28 to 0.30. Okay, so 0.28 to 0.30 meter cube per cubic meter of concrete, it has to be reduced. But if the complicated shapes are less and reinforcement concrete with clearance is increased from 60 to 200 mm, okay, then we can increase this also, the aggregate content, from 0.3 to 0.33 meter cube per cubic meter of concrete. And also if it is further simple, okay, the shapes are further simple and the minimum reinforcement with clear spacing is more than 200 mm, okay, so in that case we can further increase the aggregate content also from 0.32 to 0.35 meter cube per cubic meter of concrete. So this these criteria can be adopted. Okay, so ranking on the basis of tests for self compactability, the level of resistance at obstacles is varied for tests in the three ranks. Okay, so for the three the various types of obstacles and resistance, okay, so they are varying, and that's why the self compactability parameters are also ranked differently. Okay, so here are some of the the basic tests, the important ones we will go now. So here we will say, as you can see, it is a fillability test for concrete using a U-shaped container. So there is this one, a complexity or barrier that can be changed depending on the reinforcement in structure. So it is set up for testing flowability and segregation resistance. It is installed between the truck and the pump, and it can be used for quality control of all the concrete used. Okay, so this is basically a fillability test where there is some barrier. So based on removing this, we can see how much it is like how much flow it is able to do in the reinforcement. So as you can see here, there are three this one, four reinforcement bars at the rate at 50 mm this one spacing. Okay, so there is three shown, one more is there, so basically 200 mm, right? Sorry, three are there, so there are four this one 50 mm spacings. Okay, so total is 200 mm. Okay, so we will go in more detail into this, and all those I think these the code specification use this IS 1199. Okay, part 6. So we'll go. So basically if you remember, I told you that the flow in this one, the SCC slump flow value is almost 10 times to the normal concrete. Okay, so this table lists the measure this one values. Okay, between which standard values between which the parameters of self compacting concrete should come. Okay, in terms of fresh concrete properties. Okay, so the slump flow should be between 650 to 800 millimeter, okay, in between, and results have found that it comes around 710 mm. Okay, the V funnel, okay, which is I think used for viscosity, we will go through. So the V funnel is basically used for viscosity checking. So it should come between 8 to 12 seconds, and 7 seconds is found. And L box, okay, so this is also one of the I think passing or filling this one test. So this should come between 0.8 to 1. Okay, and results have also found similar values. Okay, so let us now go to the next lecture on self compacting concrete. So these are the four criteria for, as I told you, for which we need to test. Okay, this one, that's the SCC, self compacting concrete, and find the values whether they are coming between this range or not. Okay, so the concrete mix can be classified as SCC only if it possesses the following characteristics: the filling ability, passing ability, segregation resistance, and viscosity. Okay, we already discussed every parameter. We will go into the tests. Okay, so filling ability, that is also called as flowability. Okay, so it is the ability of fresh concrete to flow into and fill all spaces within the formwork under its own weight, which is that is the basic this one basic meaning of self compaction. So IS 10262 recommends slump flow test to assess the flowability of fresh SCC in unconfined condition. So if you remember the first class, there we discussed that there are three types of tests for finding the workability. Okay, so one is this one, the slump flow test. One was basic slump test, cone test, and the third is the VB test. Okay, so the VB test is basically used for very stiff concrete, and this one, the slump cone test, is used for normal concrete, and the concrete which flows, which is highly workable, there slump flow test is used. So as SCC belongs to the highly workable category, so there here we will be using the slump flow test. Okay, as per IS 10262 recommendations. Okay, so visual observations during the slump flow test provide additional information on the segregation resistance and uniformity. Okay, so all this can be observed visually during the slump flow test. Okay, so what is slump flow? So it aims at investigating the flowing ability of SCC. Okay, so it measures flow spread, diameter of spread. Okay, it indicates the free unrestricted deformability of the concrete, and it recommends value for slump between 650 to 800 millimeter, as we saw in the table. Okay, 650 to 800 mm. So between this range only the slump flow value should be present. Okay, now as you can see here, you can this is a depiction of the slump flow test. Okay, which has been carried out. Now we will see how it is done. Okay, so how to perform the slump flow test? Basically, we first initially place the this one, the base plate, okay, on a flat and horizontal surface, and ensure that the surface is perfectly horizontal using a spirit level. Okay, so we first place the base plate horizontally, and see that it is completely flat and also horizontal using a spirit level. So we place the cone within the 210 mm circle. Okay, on the base plate centrally. Okay, from the center we place the cone within the 210 mm circle. Okay, then we fill the cone in one operation without any hesitation or mechanical compaction. So thereafter we pour the concrete from the top, and we don't use any compaction or agitation or any methods of vibration. So directly we pour at one go. Okay, then we allow the fill cone to stand for not more than 30 seconds. So within 30 seconds we have to remove the cone. Okay, and how it is removed? We lift the cone vertically in 1 to 3 seconds at one go without interfering with the flow. So we'll remove it from the top. Okay, by lifting it in within 1 to 3 seconds. Okay, and we don't interfere with the flow in any way. Okay, so this is how it is performed. Okay, and then we will now see how the measurements are taken. Okay, so after the flow stabilizes, we measure the largest diameter of the flow spread and record as D1. So as you saw here, so we find the direction where the largest flow occurs, say for example this direction, and we measure this one flow. Okay, spread. So this is basically the D1 value. Okay, and this is basically the largest diameter value. Then we measure the diameter of the flow spread at right angle to D1. Okay, and say for example if we have measured this way, now we will measure at 90 degree. Okay, so this way, so it will be D2 diameter. Okay, and thirdly we will see that the difference between D1 and D2 does not exceed 50 mm. So this is one of the parameter we have to check. Okay, so it should not be exceeding 50 mm. Okay, otherwise there will be some type of other issues. Okay, like segregation or other factors may come into play. It will not be homogeneous. Okay, and then we report the slump flow, which is the mean of D1 and D2. That is basically we take the average. We check the concrete spread for signs of segregation. So that is as we saw in the last slide. So we basically go for this one, visual visual observation of segregation, resistance, and uniformity. Okay, and then if T500 is also needed, okay, so that is basically the time taken to reach the 500 mm circle. Okay, so for reaching the 500 mm circle, if we also need to find out, so we need to start the stopwatch immediately when the cone loses contact with the base plate. Okay, so just as we lift up, we have to start the stopwatch immediately and record the time taken for the concrete to touch the 500 mm circle first. Okay, so the time taken for the concrete after removing the lifting the this one cone to the time taken for the flow to touch the 500 mm circle first. Okay, so that is basically the T500 value. Okay, so if we are interested, we can check that also. Now according to the Indian specifications, okay, so various the slum flow can be again categorized into various various categories. Okay, so these are used for various range of applications. Okay, if if we require appropriate if we require a flow which is appropriate for light reinforced structures, okay, like casting by pump injection systems, tunnel linings, piles, foundations. Okay, so for very light reinforced structures, so we can reduce the flow. Okay, so we can reduce the flow from 550 to 650 mm, which is category SF1. Okay, again if we want to increase the value, okay, so if we want for normal application like walls and columns, so we can little bit improve the increase the slump value from 660 to 750 mm say, so that is categorized as SF2. Okay, and if we if we need for vertical application in heavily reinforced structures with complex shapes or filling, okay, under formwork, so in those cases, okay, where there is very high density of reinforcement and other complex shapes, so there we have to have very high this one the slump value, so that will come in the SF3 category, where the slump value is from 760 mm to 850 mm. Okay, so these are basically the types of slump flow ranges. Okay, so that is all about filling ability or flowability. Now let us go to the passing ability. Okay, so passing ability can be basically defined as the capacity of the fresh mix to flow through confined spaces and narrow openings such as areas of congested reinforcement, okay, without segregation. So basically passing ability is to pass through congested reinforcement without segregation. So IS 10262 specifies L box test, okay, for checking passing ability. So L box test is basically used as per IS 10262 for checking the passing ability value. Okay, so for this purpose we use the L box test for checking the passing ability. So there are two variants based on the type of gate. Okay, so one variant is using like one gate uses 3 smooth bars, okay, and the other uses 2 smooth bars. Okay, the gaps are 41 and 59 mm respectively, and the diameter of the bar is 12 mm. Okay, so 3 bar test is normally preferred, okay, as it simulates more congested reinforcement, because our aim is to find out the passing, okay, of the SCC through a congested reinforcement without segregation. So more will be the congestion, better will be the testing. Okay, so all these are given in IS 1991199 part 6 2018, as I mentioned. So for further details you can refer the code. Okay, so this is a schematic representation of the test of the L box test. Okay, so how to perform the L box test? Firstly, we place the L box on a level base and check for horizontality using spirit level, similar to the other the initial like the this one the flowability slum cone test. Okay, so slum flow test, sorry. So then we close the gate between the vertical and horizontal sections. So there is a gate. Okay, we close the gate. We pour the concrete from the containers into the filling hopper of the L box without any hesitation or mechanical compaction. So it is similar to the last test. Okay, we open the sliding gate fully in a smooth continuous action to flow the concrete to allow the concrete to flow into the horizontal section. So we thereafter basically slide the gate, okay, in a smooth continuous action, okay, to for allowing the concrete to flow into the horizontal section. Okay, thereafter we check for any signs of segregation, okay, such as a layer of cement paste mortar and segregated coarse aggregate at the top. Okay, So from above only we check it, like whether any signs of segregation and other deposition of any core segregate less cement paste mortar is there. Okay, from the top we observe. So what are the measurements we take? Okay, so we determine basically two measurements. Okay, the mean depth of concrete in the vertical section and the mean depth of concrete in the horizontal section. Okay, so we determine the mean depth of concrete in the vertical h1. Okay, this is the this one mean depth, and horizontal sections of box h2. Okay, here as you can see, right? So and mean depth at this one three positions equally spaced across this section. So this h1 and h2 value also, they are taken at three this one equally spaced across the section positions. Okay, so they are taken at three positions which are equally spaced to get even a further mean value. So this ratio is a measure of the blocking behavior of STC. So through the reinforcement, how the this one passes, the STC passes, so it measures the blocking behavior. Okay, so recommended range of the ratio is 0.8 to 1.0. So the passing ability ratio, which is h2 by h1, h2 by h1. Okay, so it should have a value between 0.8 to 1.0 for it to be called a self compacting concrete. Okay, so that is basically the passing ability. So we have gone through flowability test, okay, which is done by slump flow test. Then we have gone through passing ability, which is done by L box test for checking the segregation through congested reinforcement flow. Now we shall come to this one, segregation stability. Okay, stability testing, that is again for segregation resistance also. So this is the ability of fresh concrete to remain homogeneous in composition. It is usually assessed by performing sieve tests. Segregation resistance is important with higher slump flow classes and or the lower viscosity classes. Okay, so it is the ability of fresh concrete for remaining homogeneous composition. Yeah, it is usually assessed by performing the sieve test, and segregation resistance is important for higher slump flow classes, as we just studied, where the VMA comes into picture, and all or the lower viscosity classes. Okay, so that's why the VMA is important. So how to perform the sieve test? So here basically we perform the sieve test. Okay, so after preparing the sample, the fresh concrete is allowed to stand for 15 minutes, and any separation of bleed water is noted first. Okay, so first we prepare the sample, then it is allowed to remain untouched for 15 minutes, and then we see the bleed water, okay, which is separated above. A known weight of the sample is then poured into a sieve with 4.75 millimeter openings, which are known as apertures. So after waiting for 15 minutes and noting the bleed water separation, then a known weight of the sample is poured into a sieve having 4.75 mm opening apertures. Okay, so after 2 minutes, weight of the material which has passed through the sieve is recorded. Okay, so after pouring and waiting for 2 minutes, then we see, okay, we measure the weight of the material which has passed through the sieve. Okay, and from that we find the segregation ratio, basically SR, which is calculated as a proportion of the sample passing through the sieve. Okay, so doing this experiment we find the segregation ratio, which is basically the passing of the material through the 2 mm 4.75 mm sieve divided by the actual amount of weight used, okay, in the testing, okay, poured into the sieve. So the segregation ratio, it also has it is also classified into two ranges, okay, SR1 and SR2 as per the Indian specifications IS 1199 part 6. So if we need this one, if it is used for thin slabs and for vertical applications with a flow distance of less than 5 meter, okay, and a confinement gap greater than 80 mm, okay, so then we can, it is allowed of it is allowed to have segregation resistance of 15 to 20%. So for thin slabs, vertical application, having flow distance of less than 5 meter and confinement greater than this one 80 mm, we are allowed to have a SR value of 15 to 20%. Okay, but if the vertical applications has a flow distance of more than 5 meter and a confinement gap is less than 80 meter, then it should be less than 15%. Okay, and if the flow distance is more than 5 meter, and SR of less than 10% is also further recommended. Okay, so basically if the this one is flow is less than 5 meter and confinement gap is more than 80 mm, then we are allowed to have 15 to 20%. Okay, so that is the SR1 category. But if the confinement gap is less than 80 and the flow is also 80 mm and flow is also more than 5 meter, then we need to have a very good this one segregation resistance, that is it should be lesser than 15 or preferably even lesser than 10%. Okay, so that is all about this one, segregation. Okay, now let us come to viscosity. So concrete with a low viscosity will have a quick initial flow and then stop. Okay, and concrete with a high viscosity may continue to creep forward over an extended time. So that is the basic use of viscosity. Okay, so viscosity, if it is low, then there will be quick initial flow and then it will get stopped. Okay, the flow will get stopped. But if there is the viscosity value a higher range, okay, then it will consistently try to go forward. Okay, even after a certain point in time when the low viscosity concrete will stop, still it will the high viscosity concrete will still try to move forward. Okay, the viscosity of fresh SCC is normally assessed using the V funnel test. Okay, as I mentioned you maybe somewhere. So the basic four tests. Okay, so as you saw, the filling is mainly the flowability, that was mainly done by the this one, the flow the slump flow test. Then second was the passing. Okay, passing ability, so that was mainly done by the L box test. Third was the segregation resistance or stability, so that was mainly done by the sieving test. And now we are coming to this one, the last is the viscosity. Okay, so viscosity is basically done by the V-shaped funnel test. Okay, so a V-shaped funnel is filled with a given volume of fresh SCC, and the time taken for the sample to flow out of the funnel is measured and recorded as the V funnel flow time in V funnel. Okay, so that is basically the V funnel test, where a given volume of fresh SCC is filled in a V-shaped funnel, and the time taken for the sample to flow out of the funnel is measured and recorded in as the V funnel flow time. Okay, which should come in a certain range of I think 8 to 12 seconds. Okay, as we discussed in the table. So V funnel time is also a measure of flowability of SCC. Okay, so because viscosity is a this one, it is opposing the flowability, so therefore we have to find out that in terms of flow. So it is a measure of the time required for the flow. Okay, so as you can see here, it is the specification, the standard dimension of the V funnel. So how to do the V funnel test? The test gives the time for a certain volume of concrete to pass through a narrow opening. Okay, so this is the narrow opening and we have to fill here. Okay, so it gives an indication of the filling ability provided that blocking and or segregation do not occur in between. Okay, the concrete sample of about 12 to 14 liters is taken and poured. Okay, and the recommended value is between 6 to 12 seconds. Okay, so I mistakenly told it to 8 to 12. It is between 6 to 12 seconds. Okay, so how it is done? So it consists of two parts, as we have seen. So one is the V-shaped top. Okay, and second is the rectangular bottom. Okay, so the V-shaped top is connected to the rectangular bottom. Okay, and in the down beneath the rectangular bottom there is a gate. Okay, gate is present at the bottom of the this one, rectangular bottom or the apparatus. Okay, so how to perform the V funnel test? Initially we close this gate and pour the sample of concrete into the funnel at one go without any hesitation or mechanical compaction. So as we have seen, we in all the tests there is no use of any hesitation, compaction or any vibration. Okay, so after 10 seconds plus minus 2, okay, open the gate quickly and measure the time from the opening of the gate to when it is possible to see vertically through the funnel. Okay, so initially we pour the concrete. Okay, and then we quickly, after 10 seconds, we quickly open the gate. Okay, and then we measure the time from the opening of the gate to the time when we can see through, completely from vertically through the funnel. Okay, from top we can see what is there in the bottom. Okay, so the time taken for that after opening the gate we have to measure. Okay, so based on the viscosity timing, okay, there again the Indian specification can classify two types of SCC. Okay, so if the V1 time is less than 8 seconds, okay, so that is a that means it has a very good filling ability, okay, because it can move quite fast. So the viscosity is the viscosity is not that high, okay. The slump is the flowing ability is quite high. So it has good filling ability even with congested reinforcement. So it can be used in the congestion if the density is high of reinforcement. It is capable of self-leveling and generally has the best surface finish. So it is of superior, quality concrete, okay. If the flow time is less than 8 seconds, okay? V funnel flow time. But if the V funnel flow time is between 8 seconds and 25 seconds, okay, then it is categorized as V2. So this is more viscous in nature, which is helpful in limiting the formwork pressure and improving segregation resistance, okay. So because the viscosity is relatively higher, so it will limit the formwork pressure and also improve the segregation resistance, okay. But the V2 level of viscosity can also show negative effects on surface finish and sensitivity to stoppage or delays between successive lifts, okay. So that is one of its problems, okay. So V2 level of viscosity, it can show negative effects on surface finish and sensitivity to stoppage or delays between successive lifts. So this it has both pros and cons, okay. So we have to see which we require. Then there is some additional test also is also there. One is called the J-ring test, okay. So it measures the ability of SCC to pass through the reinforcing steel, okay. So basically here what is happening is that there is a cone, okay, and beyond it one circular steel ring is there, okay, which is having 12 millimeter diameter plain steel bars, okay, which are fixed uniformly along the circumference, okay. The external diameter of the ring is 360 millimeter and the internal diameter of the ring is 300 mm, okay. So this is 360 and this is 300, okay. So it is of thickness of 6 centimeter, 60 mm, okay. So the J ring is used together with a flow test set up by putting the ring outside the slump cone to obstruct the flow of SCC, okay. So that is basically designed, so it is a combination of both, we can say it is a combination of both filling and passing, okay. So both have been merged here to find the time, okay, and see how this is there, okay. So how it is done, let us see. So flowing ability can be measured as the reduction in flow of SCC due to the ring, okay. Because of the ring the flow will definitely get reduced, okay. So passing ability can be indexed in terms of the difference in the height of concrete between the inside and outside of the J ring, okay. So between the inside of and outside, what is the height of concrete, that will give the value of the passing ability, okay. So that is the test. And there is one more test, okay, that is the U-box test. I think we have discussed it initially. So this is the configuration of U-box, U-shaped box. So it comprises a storing compartment and a filling compartment, okay, and an opening between the two compartments. So there is a storing compartment and a filling compartment and storing compartment, and there is an opening between the two compartments. So here we pour the initial as we can see, let us discuss the procedure. So the opening gate is closed first, which is here, okay. So it is closed and the concrete is generally filled into the storing compartment until it is completely full, okay. And this is having a height of 680 mm, okay. So later the gate is open quickly, okay. So within 1 to 3 seconds it is open. Due to hydrostatic pressure, the concrete is pushed to fill the filling compartment, okay. So because of it is having a good amount of flowability and which is present due to the because of which the hydrostatic pressure is present, so the concrete is pushed to fill the filling concrete filling compartment. So the filling height is an integrated measure of filling ability and passing ability of SCC, which is what I mentioned just now. So by checking the filling this one filling height, okay, so we will get both idea of both the filling ability as well as the passing ability of SCC, okay. And apart from that, there is one more test which is called the flow box test, okay. So flow box, this is basically a container which has 35 obstacles made with PVC, okay, having diameter of 2 centimeter. The center to center distance between the PVC obstacles is 5 centimeter. So all these center to center distances This is basically 5 centimeter, and the top portion of the container consists of filling pipe, diameter 100 mm and height 500 mm, through which concrete is poured using a funnel. Okay, so the top portion of the container, it will consist of some filling pipe which is having a diameter of 100 mm and height 500 mm, and which through which concrete is poured, okay, by use of some funnels. Okay, and the difference in height between the two sides of the container, okay, is the measure of filling ability of the SCC mix. Okay, so we will find the difference in height between the two sides. Okay, one where from where it is poured, and the one where it is this is present. So based on the obstacles, okay, and the ability to pass, okay, so it is the measure of the filling ability of the SCC mix, and the difference will in height will give us an idea about the test. Okay, so for more details you can refer to IS 1199 part 6. Okay, so now let us go to the third lecture of self-compacting concrete. Okay, so where we'll be mainly seeing how the design is done. Okay, how the SCC self-compacting concrete design is done, basically by using the code IS 10262. Okay, so we will see how the mix design is done. Okay, so the characteristics of mixed proportion of SCC: cement based paste content in SCC is high due to the need to keep good workability in low water powder ratios. Okay, so cement based paste content in SCC is high due to the need to keep good workability in lower water powder ratios. Okay, using with additional use of super plasticizers and other materials. Okay, other than that, usually the powder content needs to be increased, and the water content is restrained or kept to an adequately low level. Okay, so because the aggregate is reduced, so we have to fill it by powder and fine material, and because of that, this is increased powder content, and the water content is restrained. Okay, using the super plasticizers. So mineral admixtures are used to increase the powder content. So as we have studied in previous classes, water content is basically taken care of by using super plasticizers, and the this one powder content is taken care of by using mineral admixtures. Okay, powder or cement content. So increased paste content, okay, so it supplements the decreased volume of coarse aggregates, as I just mentioned, and ensures the required viscosity of the paste at lower water powder ratios. Okay, so both of them is satisfied by increasing paste content. Okay, decreased volume of coarse aggregate and required viscosity of the paste. Okay, both are together. Okay, then high workability. Okay, so these use high performance super plasticizers. Okay, so for high workability, as I discussed, we have to use high performance super plasticizers, and for cohesiveness, okay, for cohesiveness we have to add viscosity modifying agent or VMA. Okay, so for high workability we have to use high performance super plasticizers, and for cohesiveness we have to add viscosity modifying agent or VMA. Okay, so characteristics of mixed proportion of SCC. Okay, so from rheological or flow point viewpoint, okay, flowing viewpoint, flow property viewpoint, the fresh SCC should have low yield stress and moderate viscosity. So the base SCC we get when the fresh condition of SCC is having low yield stress and moderate viscosity. Okay, so this can be achieved by two major category of SCC mixes, that is powder type SCC as well as VMA type SCC. So we need moderate viscosity and low yield stress to obtain a good fresh SCC. Okay, from flowing point of view. So powder type SCC, if we see, it is developed from normal concretes through the use of modified mixed proportions. Okay, for a given volume of concrete, volume of coarse aggregate in SCC is less than that in normal concrete. Okay, so we have gone through all this in the last lectures. So volume of sand in SCC is higher than that of conventional concrete. Okay, because the fines are more in SCC as compared to concrete. Therefore, the aggregate is less in SCC as compared to normal concrete. Then cementitious material content in SCC is higher than that of normal concrete. Okay, so all the things are like the similar things, And water content is in SCC and normal concrete mixes is similar, as we saw in the this one in the example before. Thus in SCC a relatively lower water cement ratio, more specifically a lower water to cementitious material ratio is achieved. So because we are using powders and we are using super plasticizers, okay, so there is lower water cement ratio, okay, and or cementitious material ratio because a lot of powder is there without any effect in the workability. So the low aggregate content is essential to achieve high deformability and flow speed as they reduce the frequency of collision and the solid to solid friction. So that is the benefit of using low aggregate content. So it reduces frequency of collision and solid to solid friction. Higher sand total aggregate ratio in SCC helps to maintain moderate levels of viscosity. So that also added benefit of using higher sand by total aggregate ratio, which also was defined as S by A, if you remember in the initial classes. So increase of the paste volume of SCC mixtures is achieved by an increase in the powder content with a lower water binder W by B ratio. Okay, so paste volume increase is achieved by increasing the powder content and having a lower water binder. So more will be the binder, lower will be the water binder ratio. Okay, the powders utilized in powder type SCCs include silica fume, fly ash, and ground limestone fines with different size distribution. Okay, so the various types of powders which can be used in powder type SCCs, okay, they basically include silica fume, fly ash, ground limestone fine, okay, which are having different or various size distributions. Okay, so that is all about powder type SCC. Now let us go into viscosity, this one VMA, okay, viscosity VMA modifying type SCC. So superplasticizers and VMA are added to SCC to meet the rheological requirements. So there basically superplasticizer and powder was used. Powder basically meaning mineral admixture, and here basically superplasticizer and VMA is used. Okay, so adding superplasticizers helps in reducing the yield stress of SCC with limited influence on viscosity, because superplasticizers will increase the workability, so it will reduce the yield stress, and also it will have very limited influence on viscosity. And incorporation of VMA improves the cohesiveness of the mix because it will be more viscous. Okay, VMA are usually water soluble polymers and absorb cement particles. Okay, so they provide sufficient adhesion to the aggregate. Okay, so VMA are very much usually water soluble polymers and they absorb cement particles, okay, because of their viscous and cohesive nature, and they are provide sufficient adhesion to the aggregate. One of the industrially used VMA is Wellen gum. Okay, so we can use that as an this one VMA. In these concretes, the required workability, if concrete controlled by superplasticizer dosage, and the required segregation stability, viscosity, is obtained by the use of VMA. So required, as we discussed initially also, workability is controlled by superplasticizer dosage, and viscosity is controlled by VMA. Okay, so both has to be mixed in appropriate proportions. So now let us go to the uh, an illustrative example, okay, where we can see how the mix design of self-compacting concrete is done, okay, based on IS 10262 2019. Okay, let us see that. So here are some of the stipulations, okay, the some of the values, some of the requirements for design. So the grade is M30, the type of cement is OPC 43, nominal mean size of aggregate is 20 mm, exposure condition is severe RC, reinforced concrete, and these are the flow characteristics, okay, the SCC characteristics. So slump flow class SF3, passing ability 0.9, V funnel flow V1, segregation resistance SR1, degree of site control good, type of aggregate crushed angular, maximum cement content 450 kg per meter cube, chemical admixture type is normal, which they have, and they have used polycarboxylate ether, and mineral admixture they have used is fly ash. Okay, and these are some of the test data which have been obtained for the material proportioning. So these are almost along the standard values only. So yeah, so it, as I told you, 0.125 mm in case of fines, it is taken as 8% of the sand. Okay, so if 100 kg sand is there, so we assume that only 8 kg sand is having a size less than 0.125 mm. Okay, how it is implemented we'll see now. So basically like normal like the normal concrete design only, the target strength of the mix, okay, it should be determined using the clause 4.2 of IS 10262 2019. Okay, so using clause 4.2 we can design the this one target mean strength, and as we have discussed initially, it is the summation of characteristic compressive strength plus 1.65 times standard deviation or characteristic compressive strength plus x. Okay, whichever is higher. So the x and standard deviation values are obtained from tables 1 and 2 respectively from IS 10262, and for M30 grade the s is found to be the standard deviation is 5 and x is 6.5. Okay, so basically the f target prime value will be 30 plus max of 1.65 into 5, 6.5, which comes to be about 38.25 megapascal. Okay, so again so we have found the target mean strength, okay, for design. Now let us find out the approximate air content. Okay, so again as per the table 3 of IS 10262, the approximate amount of entrapped air is 1%, okay, for 20 mm nominal maximum size of aggregate. Okay, as we have seen. Okay, so they have considered 20 mm NMSA, so for that 1.0% is prescribed for entrapped air as per table 3 of 10262 IS. Okay, so then as we know we have to find the water cement we have to find the this water cement ratio based on the strength. So FCK prime value is 38.25, and from figure 1 the free water cement ratio comes to be 0.43. okay, from figure 1 of IS 10262, and this value has to be checked with the table 5 requirements of IS 456, which suggests a maximum value of free water cement ratio as 0.45 for severe exposure of RC, reinforced concrete. So our value is 0.43, which is less than 0.45 maximum value, so it is okay. Now from that, okay, let us assume that our water content is 195 kg per meter cube. Okay, because it has been mentioned that it should be between 150 to 210 in case of SCC. Okay, so let us measure it to be, assume it to be 195. So using water cement ratio is 0.43, the corresponding cement content has come to be 453. Okay, so they have assumed the water content to be 195, and they have taken the water cement content as ratio as 0.43, so the corresponding cement content comes to be 453. Okay, so now if we are using OPC and fly ash, okay, and we assume that fly ash is around 25 to 50%, that is basically we have taken 40%. So if we assume 40% of fly ash and 60% of OPC out of the 453 cement content kg of cement content, so we will find that this 60% of OPC of 453 will come to be around 271 kg per meter cube of OPC, and 40% of 453 will come around 182 kg per meter cube of fly ash. Okay, so 271 kg and 182 kg of OPC and fly ash is found, okay, for a total of 453 cement content. Now selection of chemical admixture. Okay, so let us assume that the dosage of chemical admixture is 0.6% by mass of cementitious material. Okay, so because the cementitious content has been found to be 453, so 0.6% will come to be about this one 2.71. okay, so 2.71 is the kg per meter cube is the amount of PC plasticizer, carboxylate ether plasticizer to be used. Okay, so now let us select the powder content. So powder content basically is the total of OPC, fly ash and the sand component, which is 0.125 millimeter small. Okay, so powder content corresponds to the fines less than 0.125 mm. So basically it will be OPC, fly ash and sand component finer than 0.125 mm. Okay, so selection of powder content is based on the classes of segregation, resistance and viscosity. So based on this the powder content is selected. The typical range for powder content in SSC is 400 to 600 kg per meter cube. So basically powder content should be in the range of 400 to 600 kg per meter cube, okay, and which is adequate for self-compacting concrete, and mix corresponding to SR1 and V1 is needed, okay. So the mix should be adequately cohesive. That's why, because SR1 V1 requires this, that the mix should be cohesive, and uh, we have assumed here the powder content is 520 kg per meter cube, because it should be between 400 and 600. So let us assume 520, okay. So 520 is the required powder content, and we have got cement content was 271, 60% of that 4, I think 453, yeah. So it was 271 and fly ash was 182. So we have to minus 182 and 271 from 520, and we get 67 kg per meter cube of fines, that is sand, okay, which is having size less than 0.125 millimeter, okay. So that this sieve analysis, okay, sieve analysis has like, this is a standard, it has been found to be a standard value, that sieve analysis gives 0.125 mm passing fine as 8%, okay. So if we, as I told you, if we take 100 kg, we'll get only 8 kg sand which is passing through 1.125 mm, okay, sieve. So therefore for 67 kg of sand passing through 0.125 mm, we have to take sand content as 65 divided by 0.08, okay. So it will come around 838 kg per meter, okay. So therefore if we take 0.8 of 838 plus 182 plus 271, we will get the powder content of 520 kg, okay. So now by using the concept of specific gravity, volume and all, if we equate, we will find the volume of coarse aggregate as 0.31 meter cube, okay. So then this is the normal calculation procedure, and we have to say, we have to use this for finding the amount of coarse aggregate to be added. So the mass of coarse aggregate to be added is 0.31 times 2.74 specific gravity into 1000 kg per meter cube, the space this one density of water, so which is 849 kg per meter cube. So mass of coarse aggregate has come to be 849, okay, which is generally in normal concrete around 1100 200 something like that, okay. So it has reduced. Now calculating the total powder content. So here if we see the volume of powder, okay, so that is basically the volume of OPC plus fly ash plus fine aggregate finer than 0.125 mm, as we know. So that comprises the powder content. So calculating the volume, okay, so calculating the volume, we get the volume as 0.194 meter cube, okay. So volume of powder is 0.194 meter cube, and ratio of water to powder by volume. So water, we assume it to be this one 195, if you yes, 195 kg per meter cube. So if we see here, so it is this one 195 ratio of water to powder by volume, okay. So that will be 0.195 by 0.194, okay. So this one the value will be around 1, okay. So it will be slightly more than 1, but 1, okay. So recommended range for the ratio is 0.85 to 1.10, okay. So the recommended range of this one the recommended range for the ratio is 0.85 to 1.10, and because 1 is between them, so as per IS 10262 the value is okay. So from there the mixed proportion for trial 1, we get the these as the quantities, okay. So this is how the mixed proportion is done. So the total coarse aggregate content may be proportion between 20 and 10 mm sizes, okay, based on sieve analysis and particle size distribution, such that an overall grading curve satisfies the table 7 of IS 383, okay. So this is basically the consequence, and as per like our fundamentals only, we know that 20 and 10 mm size in between, we have to proportion the coarse aggregate passing as per the curve mentioned in table 7 of IS 383, okay. So finally we have to do the trial test and final mix design. So slum, we have to use slum flow, L box, segregation resistance and V funnel test needs to be carried out to ensure that the mix meets the necessary flow and viscosity requirements as for the SCC. If satisfactory performance is not obtained, the mix should be redesigned, okay. So that is a basic norm. And based on the trials, there could be a need to add VMA to improve the cohesiveness of the mix. So if the trials are not not found satisfactory, we need to add VMA and other super plasticizer or other stuff for improving. For cohesiveness we have to add VMA, and for other requirements we can go for super plasticizer and powder addition. Okay, so through this we can basically take care of the issues which we have discussed here. Okay, so with this we come to the end of this week's course. So now let us go to the solve problems. Okay, so first question is, in the context of placement of normal fresh concrete, which of the following options is incorrect? Okay, the lack of vibration in the freshly placed concrete mass could result in the honeycombing of concrete. The closely spaced reinforcement increases the chance of honeycombing. Form vibration is very effective when the member sizes are large. The over vibration of freshly placed concrete could lead to segregation of concrete. So if we see all first, second and fourth option, three are correct. Lack of vibration results in honeycombing. Over vibration leads to segregation. Close space reinforcement also increases honeycombing. Okay, but form vibration, okay, so that is mainly the use of external vibrators, and it is mainly used in high density concrete. Okay, so it is nothing to do with member size. Okay, so the third option is incorrect. Okay? So as you can see, form vibration is very effective when the member sizes are large is the correct option. Second question, in the context of self-compacting concrete SCC, consider the following statements. Statement 1, SCC is a flowing concrete mix that does not require external compaction effort and consolidates under its own weight. So this is true. And statement 2, the SCC is prepared in such a way that there is no segregation, and at the same time there is enough fluidity for easy placement of the concrete. Okay, so that is also true. Okay, so no external compaction effort is required, consolidates under its own weight, no segregation. Okay, and at the same time enough fluidity for easy placement. Okay, so both the statements are true. Third option is correct. As you can see, both of statements are true. Let us go to the third question. In the context of self-compacting concrete SCC, which of the following options is incorrect? Okay, the self-compacting concrete SCC is able to pass through congested reinforcement more easily compared to normal concrete. The use of SCC can reduce the noise pollution in a construction site. Use of SCC eases placement and hence saves time and manpower. SCC is characterized by very low powder and fines content. So if you see, SCC is able to pass through congested reinforcement more easily compared to normal concrete. That is true. The use of SCC can reduce the noise pollution in a construction site. That is true, because no external compaction equipments are required. Use of SCC eases placement and hence saves time and manpower. That is true, because of its high flowing and compacting ability. And SCC is characterized by very low powder and fines content. So that is incorrect, because it is characterized by very high powder and fine content. Okay, so the fourth option is the correct option. Okay, so as you can see, SCC is characterized by very low powder and fines content is the correct option. Let us go to fourth question. In the context of properties of the mortar and aggregate phase in the concrete, consider the following statements. Statement 1, the phenomena such as segregation and aggregate interlocking in the fresh concrete are solely related to the concentration of the aggregate phase in the mortar. Statement 2, the carrying capacity of the mortar phase is defined as the critical maximum volume of coarse aggregates it can hold without segregation and aggregate interlocking in the fresh concrete. So the first statement is incorrect, because the phenomena of segregation and aggregate interlocking in fresh concrete are not only related to aggregate phase but also depend on the binder. Okay, binder and the filler. Okay, so more is the binder filler. Okay, so better is the less is the chance of segregation and better is the carrying capacity. Okay, so the first option statement is wrong, and the second statement is carrying capacity of mortar phase. So that is true. So it is defined as the maximum volume of coarse aggregate which it can hold without segregation. Okay, and aggregate interlocking. So the second statement is true. Okay, so 1 is false and 2 is true. So the second option is correct. So as you can see, statement 1 is false and statement 2 is true. Okay. Fifth question. In the context of chemical admixtures used in the self-compacting concrete SCC, Consider the following statements. Statement 1, superplasticizers are used in SCC to reduce the water demand of concrete, or in other words, it helps in increasing the powder content at a given water content without compromising the compromising the workability of the mix. Okay. And statement 2, the use of viscosity modifiers is done to reduce the viscosity of the fresh concrete paste and to make the concrete more flowable. Okay, so one is true. First statement is true. Superplasticizers are used for reducing the water demand of SCC as well as in normal concrete. Okay, and it increase, therefore because the water is less, so the powder content it will get increased. Okay, because of addition of this one. Okay, because the water content will be less and the cement content will also be less, so they will use fly ash and other forms of admixtures, so which will increase the powder content at a given water content without compromising the workability of the mix. So one is true, but viscosity modifiers is used for increasing the viscosity, not reducing. So that generally reduces the concrete flow. Okay, so statement 2 will be incorrect. So 1 is true and 2 is false. So first statement will be correct. So statement 1 is true and statement 2 is false. Sixth question, in the context of SCC, let us consider following statements. Statement 1, the amount of coarse aggregate is lower in SCC compared to normal concrete. So this is true. In SCC, coarse aggregate content is lower as compared to normal. And statement 2, the amount of cement content is much higher in SCC compared to normal concrete. So that is not correct, because cement content is almost same, but the powder content is high. Okay, in SCC. So cement content is almost the same, powder content is high in SCC, but the amount of coarse aggregate is low in SCC as compared to normal aggregate. So 1 is true and statement 2 will be false. Okay, so first option is the correct option. So as you can see, 1 is true and 2 is false. Seventh question, in the context of self-compacting concrete SCC, consider the following statements. The first statement, the filling ability or flowability of the concrete is defined as the ability of fresh concrete to flow into and fill all spaces within the formwork under application of adequate external vibrating effort. Okay, so this is completely wrong, because SCC does not use any external vibrating effort. So first statement is wrong. Statement 2, according to IS 10262, slump flow test can be used to measure the flowing ability of SCC, and the recommended values for slump flow are 650 to 800 mm for SCC. So as we just discussed in the table, so the standard value of 650 to 800 mm is desired for SCC, and it has been taken from IS 10262. So first statement is wrong and second statement is true. So statement 1 is false and statement 2 is true. The second option is correct. So as you can see, 1 is false and 2 is true. Eighth question, which of the following test is best suited for measuring the viscosity of the self-compacting concrete? So slump cone test, L-box test, J-ring test, or V-funnel test. Okay, so if you remember a slump cone test, okay, so this is mainly for filling ability, L-box test is mainly for passing ability, J-ring test is a combination of both filling and passing, and V-funnel is basically used for the viscosity. Okay, so V-funnel test, that is the fourth option, is the correct option. So as you can see, V-funnel test is the correct option. Ninth question, which of the following options correctly represents the recommended range of the passing ability of compacting concrete tested using L-box? Okay, so what is the ratio? Okay, passing ability ratio which is recommended for SCC. Okay, desirable value, is it 0 to 0 0.2, 0.5 to 0.8, 0.8 to 1, or 0.5 to 1? So if you remember, 0.8 to 1 is the value. Okay, so the value is the ratio between H2 by H1, so it should be coming between 0.8 to 1. So third option is the correct option. So as you can see, 0.8 to 1 is the correct option. Last question, in the context of sieve test done for finding the segregation resistance of concrete, consider the following statements. Statement 1, the fresh concrete is allowed to stand for 15 minutes prior starting of the sieve test, and then that fresh concrete of known mass is poured into the 4.75 mm sieve. Statement 2, the amount passing through the sieve is noted and the amount retained on the sieve is calculated. The segregation ratio is calculated as the proportion of the sample retained on the sieve. So if you see the first option, the first statement is correct. The fresh concrete is allowed for 15 minutes standing prior to sieve testing, and fresh concrete of known mass is poured into the 4.75 mm sieve. That is true. But the second statement, so that is not correct. The amount passing through the sieve is noted, and the amount retained of the sieve is calculated. So only the amount passing is only calculated, okay, and the segregation ratio is calculated as the proportion of the sample which is passed, okay, on the sieve, not retained. So second statement, that is basically not incorrect, that is not true. So one will be true and two is false. So first option is the correct option. So as you can see, statement is one is true and statement two is false, okay, so that is the correct option. So yeah, so with this we come to the end of our this week's course. So we will go to the 7 week course, 6 weeks lecture next class. So if you have any questions for this class, you can ask, or otherwise we can sign off. Okay then, so if you don't have any queries, so let us end the discussion today. Thank you.